Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 5 on the topic entropy in the first module of the subject thermodynamics and thermal engineering. Let's have a quick recap of what we have discussed in the lecture number 4, that is the previous lecture. We started with definition of a thermal energy reservoir. What is a thermal energy reservoir? It is a body of infinite heat capacity which can provide large amount of heat. At the same time, it can also absorb large amount of heat. The body which provides infinite quantity of heat or large amount of heat is termed as the source, and the body which can take a huge quantity of heat, that is to which the heat is rejected, is termed as sink. Then we have seen what is a heat engine. It is a device which is operating between a source and a sink. The source is a high temperature one, sink is a low temperature one. By operating between these two temperature limits, it produces useful work. The engine takes some amount of heat from the source, converts portion of the heat into useful work while rejecting the remaining heat to the sink. So the difference between the heat supplied and the heat rejected is the net work produced during the cycle by the engine, and the Q1 is the amount of heat supplied and Q2 is the amount of heat rejected, or it can be QH and QL. The notations can be different, but the concept remains the same. So next, this forms with this basis the Kelvin-Planck statement was formulated. It clearly says that for any device to operate between a source and a sink, there must be two reservoirs. Source also should be there and sink also should be there. We cannot operate an engine with either with a source or with a sink. So if it is so, it is violating the Kelvin-Planck statement of the second law of thermodynamics. Next, we had seen the principle of the refrigerator and a heat pump. What is the desired effect in case of a refrigerator? What is the desired effect in case of a heat pump? In case of a refrigerator, the amount of heat removed from the space, that is the refrigerated space, that is the focus, that is the desired effect. And in case of heat pump, how much heat has been rejected to the surrounding, that is the desired effect. In case of refrigerator and heat pump, the work has to be supplied to the system. Work is done on the system. It is not a work producing device, it is a work absorbing device. So the output, the performance evaluation of the refrigerator and the heat pump is expressed in terms of coefficient of performance, which is the ratio of desired effect to the work input to the system. The system, it could be heat pump or refrigerator. And we have seen the COP of a heat pump in terms of COP of refrigerator, that is COP of heat pump is equal to COP of refrigerator plus 1. If you know the COP of refrigerator or heat pump, we can find the COP of the other device. So then we have solved numerical questions pertaining to heat engine, one problem related to the refrigerator, heat pump, and there was one numerical question like an integrated cycle where the power output or the work done by the heat engine is used to drive a heat pump. The heat engine is operating between T1 and T2 temperature. T1 is source temperature and T2 is the sink temperature, and that output of the engine is used to drive the heat pump, which is operating between the temperature limits T3 and T4, and we have determined the amount of heat rejected by the heat pump. So now let us move to the contents in the lecture number 5. Development of entropy, how the concept of entropy has evolved. Clausius inequality, it is a very important one. Entropy, then entropy change, and we will be solving some numerical questions. We will be solving some numerical questions based on the entropy changes and Clausius inequality. So let us start with the development of entropy. If you look at this schematic, there is a reservoir, high temperature reservoir. T suffix RES. RES stands for reservoir, which supplies del Q amount of heat. So, this is the source, this is the reservoir which is the heat supplied, this portion is the heat supplied. Heat supplied to the reversible heat engine, a reversible heat engine. So, the last lecture itself told this reversible engine is a one whose process can be reversed, and it is high, its efficiency is higher than a irreversible engine. Any device which is a reversible one, which is the performance of the reversible device is always higher than the irreversible device. The irreversible devices, either a heat engine or a refrigerator or a heat pump, it has its own losses. So, the efficiency or the coefficient of performance of the system comes down. So, now and also for a reversible device, QH by QL, that is heat supplied at high temperature source and heat rejected at low temperature sink, that can be equated to that is equal to TH and TL. So, that is also there. So, in one of the numerical question I wrote TH as replace TH and TL in terms of T3 and T4, the equivalent temperatures. So, here the reservoir supplies heat, this is the source, it provides del Q amount of heat from the reservoir supplied to the reversible heat engine. So, since it is reversible heat engine, I am using the word REV. If this term is not there, that means the device is an irreversible one. So, simply it is a heat engine. So, it is producing del W reversible amount of work. So, as per the Kelvin-Planck statement, it has to reject some amount of heat. It cannot convert the entire del Q amount of heat into useful work. So, it is not possible. So, the amount of heat rejected, that is del Q. There is a engine here. I have taken a combined system, like an integrated system, a system and a reversible heat engine, RHE, and a reversible. So, the combined system here refers to the system and a heat engine, reversible heat engine. So, the system is, it could be like a piston cylinder arrangement, it is a piston cylinder arrangement which I have considered as a system, and the reversible heat engine is operating between this device and the reservoir. The reservoir is a high temperature source, and this combined devices, the devices, that is both the system and the reversible heat engine, is the combined system. So, this is the which is represented by a dotted line. Now, let us see, let us do a small derivation how this concept of entropy has evolved. Now, for a reversible heat engine, RHE, or we can write like this, HE reversible. So, here if you see the amount of heat supplied is del Q RES, del Q RES is the reservoir divided by the amount of heat rejected is del Q. Let me use the same representation, del Q RE is the heat supplied and this is the heat rejected, del Q. So, this will be equal to, replace Q by T, that is temperature of the reservoir by T. Here I have taken the temperature as T reservoir, here I have taken the temperature as T only. So, let us this be equation number 1. So, if we rearrange equation number 1, so bring this temperature of the reservoir to the left hand side. So, it becomes del Q of reservoir divided by T of reservoir is equal to this del Q term, which is on the left side of the denominator, I am bringing to the right side numerator. So, del Q divided by T. So, this is, let this be equation number 2. Let this be equation number 2. Now, I am going to apply the first law of thermodynamics for this combined system. Okay. Applying the first law of thermodynamics, del W is equal to del Q RES minus change in internal energy or total energy of the system. Let me use the same representation. Del Q, that is the total work done of the combined system. The combined system work quantity is equal to the heat quantity and this one, that is Q equal to W plus delta E. So, that I have rearranged Q equal to D plus delta E. So, that let us take minus delta E. So, here let me use the same symbol. This is total dE total. So, here if you see, del W total is the total work of the combined system. What is the combined system here? The reversible heat engine and the system, and the piston system is the piston cylinder arrangement, and dE total is the change in total energy of the combined system. So, that is what I have taken. So, let this be equation number 3. So, this is based on this equation Q equal to W plus delta E. So, that is what based on this equation only I have rewritten here. Now, substitute the equation 2 in 3, substitute 2 in 3. What is 2? 2 is del Q reservoir by T reservoir is equal to del Q by T. So, substitute 2 in 3. So, let us, so when you substitute, this is 1. So, instead of del Q reservoir, I am substituting this term, that is this term. So, find out the value of del Q reservoir from equation number 2. So, that will be left side there is no change, delta W total is equal to T of reservoir into del Q by T. T of reservoir into del Q by T. So, that is the first term minus dE total, minus dE total. Okay. So, again let me emphasize, W total is the work of the combined system, which comprises of both the heat engine, which is of reversible type, and the system, here the system which is considered as the piston cylinder arrangement, and dE total is the total energy of the combined system. Now, let us assume the system undergoes a thermodynamic cycle, So, in the previous classes we have defined the thermodynamic cycle. A thermodynamic cycle is nothing but a series of processes. In order to have a thermodynamic cycle, minimum 2 processes should be there, and also the initial state and the final state should be similar. Suppose if you have 2 processes, 1 to 2 and 2 to 3, 3 to 1, until 3 to 1 process takes place, we cannot call it as a thermodynamic cycle. Of course, 1 to 2 and 2 to 3 are 2 individual processes. In this case, the initial state is 1, the final state is 3. So, it does not meet the requirement. So, it is not a cycle. In this case, it is 2 different processes. So, a cycle is a series of processes. Either generally we use a summation term. Suppose if you want to calculate all the work quantities or the heat quantities, instead of that we can use a cyclic integral. So, for a cyclic integral, for a thermodynamic cycle, this is for one process. So, this is for a cyclic integral of dW is equal to, okay, cyclic integral of q by T minus cyclic integral of dE total. So, this is equation number 4 and this is equation number 5. So, the difference between equation 4 and 5 is 4 is the 5 is it is for I have written the equations similar equation similar to equation number 4 for a thermodynamic cycle. This smaller circle in the integration denotes that the integration to be done over the entire cycle. That is the smaller circle in the integration, there is you will find a smaller circle in the integration term which indicates that the integration has to be done over the entire cycle, and we know the cyclic integral of a property is equal to 0, of course, Q is not a property, W is not a property, whereas in this term, in this equation, this is not a property, this is not a property, Q is not a property, whereas energy is a property of a system. So, this term can be, since E is a property, so cyclic integral of a property is equal to 0. So, this term will get cancelled, So, equation 4 reduces to, since E is a thermodynamic property, its cyclic integral is equal to 0, equation 4 reduces to, so this equation reduces to, so T temperature of reservoir is constant, we can take this one. So, T of reservoir integral of del Q by T is less than or equal to 0, whether the engine is a reversible one or a irreversible one, either of the engine cannot produce net work in a cycle by exchanging heat with a single reservoir. If that be the case, that means we are violating the Kelvin-Planck statement of the second law of thermodynamics. So, that is what it is mentioned here. Since the reversible heat engine cannot produce net work in a cycle by exchanging heat with a single thermal reservoir, that is according to Kelvin-Planck statement. So, here when I am saying the cyclic of this property, so this is 0. That means this reversible heat engine is producing this much of work by operating with a single reservoir only. That is what it is indicating, which is not possible because it is violating the Kelvin-Planck statement of the second law of thermodynamics. Therefore, cyclic integral of W total is less than or equal to 0. Therefore, cyclic integral of W total is less than or equal to 0, and this term cannot be equal to 0. Therefore, so T of cyclic integral of less than or equal to 0 and T reservoir of cyclic integral of dQ by T is equal to 0, but temperature of reservoir is not 0 or less than 0, it cannot be. There is some temperature, a positive temperature. Therefore, so this is equal to 0. So, we will write, so out of these two terms, this is, let me write total term, this is 0. So, this is the property of this one, this is a property, cyclic integral of a property is 0. So, this is 0. So, the remaining term is only this term is left. So, this is equal to T of reservoir cannot be or less than equal to 0. So, the only quantity that can be 0 is cyclic integral of del Q, sorry, let me write it clearly, del Q by T is less than or equal to 0, because this term cannot be equal to 0, So, this is that is equation number 6, This forms the basis for the development of entropy. Later this is equal to ds, ds equal to dq by t, okay, which we will see. So, equation 6 is known as Clausius inequality, which is valid for all the thermodynamic cycle, whether it is a reversible cycle or a irreversible cycle. In case if delta q divided by t is less than 0, it is for irreversible cycle. For a reversible cycle, this will be equal to 0. For a reversible cycle, this will be equal to, for a reversible cycle, the cyclic integral of, so the cyclic integral of del q by t is equal to 0 for a reversible process. If it is less than 0, it becomes irreversible. It becomes, if it is greater than 0, which is not possible, so it is for impossible cases. So, this is for a reversible, if it is 0, it becomes a reversible cycle. So, this equation is known as Clausius inequality, There is like if it is less than 0 or if it is greater than 0, so that is why there is some inequality. Next, so with this background, the term entropy has been introduced. A quantity whose cyclic integral is equal to 0, so in this case is cyclic integral of dq by t is equal to 0, depends on the state only and not on the path of the process. So, it depends upon the state of the system, that is the initial state or the final state. It does not depend on the path taken by the system from the initial state to the final state or whatever it is. Therefore, the quantity cyclic integral of dq by t must present a property. It should be a property because it does not depends on the path of this one, and that property was named as entropy by the scientist Clausius. So, that property is named as entropy. So, if you take this one, the previous one, cyclic integral of del q by t, this is nothing but ds, where s is the symbol used, s is the letter or alphabet used to represent entropy. We use h, small h to represent enthalpy, sometimes capital H also is accepted, it is used. U is used for internal energy, we use q for heat quantity, w for work quantity. Entropy is represented by the letter capital S. Suppose if it is specific entropy, specific quantity means that particular parameter divided by unit mass. Suppose if it is capital H is, we call it as enthalpy, you divide the enthalpy, if it is divided by mass, it becomes specific enthalpy means kilojoule per unit mass. So, like specific entropy is small s, generally when we say entropy it is capital S. So, this property was named by Clausius as entropy. So, ds is equal to cyclic integral of dq by t, that is equation number 7. So, ds means it is like du. When we say du, it is change in internal energy, like dt means change in temperature. So, ds means change in entropy. So, this equation number 7 represents the change in entropy for a process. It represents the change in entropy of a system during a process. It is an extensive property. Entropy is an extensive property of a system and it is represented by the letter S. It gives a measure of molecular disorder in a system. So, that is the simple definition of this entropy. And for a reversible process 1 to 2, this equation is written as 1 to 2 is initial state is 1, final state is 2. So, the change in entropy is final entropy minus initial entropy. So, that will become S2 minus S1. So, here I will mention like for a process this one, let me write it here, for a process, for a reversible process 1 to 2, this ds becomes S2 minus S1, that is the change in entropy, and integral 1 to 2, lower limit is 1, upper limit is 2, because the initial state is 1, the final state is 2, integral of cyclic integral of dq by t, So, S2 minus S1, sorry, there will not be any this cyclic integral term because that is The smaller circle is to be used only for a cycle, not for a process. For a process, when we say 1 to 2 or 2 to 3, it is just only integral without the circle, integral without the circle. So, for a process, let me write it here, process 1 to 2, I will write it again, S2 minus S1 is equal to integral of 1 to 2 dq by t, dq by t or del q by t. Del q by t, okay, del q by t. Since I am using the term del, you can use del q by t. So, if it is for process 2 to 3, the limit will be, lower limit will be 2, upper limit will be 3, I will write dq by t. So, dq by t is same only for a more than one process, that is minimum 2 process, then we use a this one. Even that for also we can write cyclic integral of dq by t between the limits 1 to 2 plus cyclic integral of dq by t between the limits integral dq by t between the limits 1 to 2 plus integral dq by t between the limits 2 to 3. Smaller circle to be used only for a thermodynamic cycle. So, this is the change in entropy, this is change in entropy of a system which undergoes a process, irreversible process 1 to 2, which undergoes a reversible process 1 to 2. This is equal to sign indicates the process is a reversible one. When we say ds equal to dq by t, that means the process is a reversible one, because that is based on the Clausius inequality. This is based on the Clausius inequality. For a reversible process, it is equal to, if the left hand side of the equation dq by t cyclic integral is less than 0, it is for an irreversible process. Now, let us see how I am writing the equation number 7. Equation number 7 is this equation, this is equation number 7. Here I am writing equal for a reversible process. For an irreversible process 1 to 2, the equation 7 will be written as, instead of equal to we have to put less than symbol, less than symbol. Do not put greater than symbol, that becomes an impossible cycle, impossible cycle. Either it is a less than 1 or greater than or equal to ds, ds equal to dq by t or less than. It is not possible to have a cycle in which ds is greater than dq by t. Okay. So, that is a impossible cycle, this one, dq by t is greater than 0. Let us consider the process is 1 to 2, dq by t is less than 0, less than 0, less than 0, and that means this is equal to ds. So, dq by t becomes less than ds, or in other words rearrange, ds is greater than dq by t between the limits 1 and 2. The entropy change during an irreversible process is always greater than the entropy transfer. So, that means the entropy change is this is the entropy change, S2 minus S1, change in entropy at state point 2, final state minus initial state. Because ds, if dq by t is less than ds, obviously ds should be greater than dq by t, like a is less than b means b should be greater than a. So, like that ds is greater than dq by t between the limits 1 and 2. So, this is the entropy change undergone by the system during the irreversible process. Whether it is a reversible or reversible, ds is the change in entropy. This is always greater than the entropy transfer. Entropy transfer is this term, heat quantity, change in the heat quantity per temperature divided by temperature. This is the entropy transfer. So, for an irreversible process, always ds is greater than dq by t, ds is greater than dq by t. Whereas, for a reversible process, it is equal. For a irreversible process, ds, let me again repeat, ds is greater than dq by t. This is because some entropy is generated due to irreversibility. Irreversibility is due to the that is the losses in the system, reversibility. If you, in simple term, irreversibility, it is the like the maximum. Suppose if you take a system, it might have got a maximum potential that it can produce work, maximum potential of work, but the actual work done by the system will be less than the maximum potential, than its maximum potential. That difference is called as the irreversibility. Let me repeat again, the maximum work potential of a system, we call it as a reversible work, that will be always more than the actual work done by the system. So, the difference between this reversible work and the actual work is referred to as the irreversibility. This difference, whatever the losses which is happening, the deviation between the actual work from the reversible work, that is termed as the entropy generation. That is termed as entropy generation. So, ds equal to dq by t plus entropy generation. If the change in entropy of a system during a process is equal to entropy transfer is del q by t, that means there is no entropy generation in the system. That is, S suffix gen is equal to 0. S suffix gen is equal to 0. If the change in entropy of the system and the entropy transfer during the process in the system are equal, then this term will become 0. The entropy of an isolated system during a process always increases, which is known as increase of entropy principle. Entropy of a system, what do you mean by an isolated system? System which has no interaction with the surrounding. There is no interaction between the system and the surrounding. For such type of systems, the entropy always increases. So, that concept is termed as increase of entropy principle. Increase of entropy principle. So, with this background, let us solve some numerical questions. Before solving numerical questions, let us have a small recap, because there are a lot of new terminologies introduced during this lecture. We saw how the development of entropy, how it has evolved. We have taken a combined system. Combined system comprises of a reversible heat engine and a reciprocating piston cylinder arrangement. That is the system. So, the combined system is a combination of these two. Reservoir supplies T RES is the reservoir which provides del Q reservoir RES amount of heat. So, then during the course of the derivation, we found that the cyclic integral of a property is 0. So, that term, the last term got eliminated. Then temperature of the reservoir cannot be equal to 0 or less than 0, because it is providing heat. So, that means it should be a positive quantity. So, the cyclic integral of dq by t should be less than or equal to 0. Should be less than or equal to 0. If it is 0, it becomes a reversible process. If it is less than 0, it becomes irreversible process. Then the new property came that was evolved, that is entropy, ds equal to dq by t. ds equal to dq by t, that is for a dq by t is equal to ds for a reversible process. And in case of irreversible, that will be less than ds, or ds will be greater than dq by t. The same equation can be applied for a process 1 to 2. So, when we are applying to a process, we should not put the small circle in the integral, because that indicates only for a thermodynamic cycle. The integration to be done for an entire cycle, not for a process. So, for a process, we know the process, the initial state and the final state. So, lower limit and upper limit, like that. And the difference between the entropy change ds and the entropy transfer is the entropy generated in the system, which is the irreversibility, which is the difference between the reversible work and the actual work done by the system. So, now let us solve some numerical questions based on these concepts. 1 kg of saturated water vapor at 100 degrees centigrade is condensed to saturated liquid. Of course, during condensation, it is a phase change process like evaporation. The pressure remains constant, the temperature remains constant. In a constant pressure process, by heat transfer to the surrounding air, the air temperature is given as 25. What is the net increase in entropy of water and surrounding? So, the mass of water is given 1 kg, mass of water is given as 1 kg, temperature is 100 degrees centigrade converted into Kelvin, temperature of the air is 298 Kelvin, that is 25 degrees centigrade. Now, first let us take the properties from the steam table, because we know this one. This is table number 1, table number, because temperature is here is given. So, in the previous class itself I told, if temperature is given, or suppose if pressure of the steam is given, we refer table number 2. If temperature is given, you can refer table number 1. So, this is table number 1. In the first column, you will have temperature, table 1. So, the given temperature is 100 degrees centigrade. So, corresponding to 100 degrees centigrade, I have taken the value of HFG, that is latent heat, 2256.9. Let us see the table. See, this is HFG, this is HFG, and this is SFG. HFG is gas state enthalpy minus liquid state enthalpy. If you subtract HF from HG, you will get HFG. Similarly, if you subtract SF from SG, you will get SFG. Okay. So, corresponding to 100, I have taken the HFG value and SFG value. Corresponding to 100, I have taken the HFG value and SFG value. So, that is what is mentioned here. HFG, this is from the steam table, this is from. Okay. Now, the first let us heat, how much is the heat rejected during the condensation process. To calculate the heat rejection, we should know the mass of the working fluid, that is given as 1 kg, into the enthalpy, into the latent heat enthalpy of in this case this condensation. So, it is 2256.9, I have rounded off to that one. So, I have taken 2257. So, this much amount of heat is rejected during the phase change from vapor to liquid. Now, I am calculating the enthalpy change for the water, So, that is mass into SFG, So, here there is one small error, it should be here kilogram. The enthalpy unit is kilojoule per kg Kelvin. So, that kg is missing. So, the error is regretted. Okay. So, it is like kilojoule per kg Kelvin. Kg is missing here. This is for this unit. So, direct formulas are there, mass into this one, like how you calculated heat rejected. So, this is 1 into this one, entropy, the change in entropy. So, SFG I have taken 6.408, that is from the steam table. So, you can simple calculations. And next, the question asked is, what is the net increase in the entropy of water and surrounding. So, we should know the entropy change of the water and the surrounding, then only we can find the net increase. So, for the surrounding, it's a standard formula Q by T naught. T naught is the reference temperature, Normally, for calculations, it is taken as 25 degrees centigrade. Even if it is not mentioned also, you can take 25 degree. In some cases, they will take it as 20 or also. But here it is given as the ambient temperature, that is 25. So, I have taken the same 25, converted into Kelvin. Do not substitute here. Here it should be, temperature should be substituted in Kelvin only, not in degree centigrade. So, we can calculate the change in enthalpy of the surrounding. The net enthalpy change is the summation of the enthalpy change, the water and the surrounding. So, this is the net enthalpy change, 1.522. It is a very simple calculation problem. So, this is what we have been asked to find. So, to summarize this problem, the net enthalpy change is equal to change in enthalpy of water plus change in enthalpy of surrounding, change in enthalpy of surrounding. Okay. This is minus m into SFG, SFG to be taken from the steam table, and this is Q by T naught or TA. Here T naught is equal to TA, ambient temperature, T naught is equal to TA. You can have TA also, okay, but generally in the standard books and all, T naught is the reference temperature, the symbol T naught is used for the reference temperature. So, this is a very simple one, so you can calculate. So, it has to be found as 1.522 kilojoule per Kelvin. When we multiply the entropy by the mass kg, the kg term and kg term will get cancelled. So, we will get, instead of kilojoule per kg Kelvin, the kg term will get cancelled. So, we will get kilojoule per Kelvin. Let us move to the second question. A rigid tank contains 5 kg of saturated vapor, that is the refrigerant R134A. R134 is tetrafluoroethane at temperature of minus 18 degrees centigrade. The refrigerant is now cooled while being stirred until its temperature drops to 1 bar. Actually it should be like minus 26 degrees centigrade, because the temperature is given. Let us take this as minus 26 degrees centigrade, minus 26 degree centigrade. Because one data is given in temperature, another is in pressure. Of course, we can find the saturation value from the table. So, let us take this minus 26, which I have mentioned. Determine the entropy change of this refrigerant during this process. Assume the dryness fraction of the refrigerant at the final state is 0.86. Let us recollect what do you mean by a dryness fraction. It is, in other words, it is called the quality of the steam. When we say it is represented by the letter small letter x, x is equal to 0.86 means it contains 86% vapor and remaining 14% liquid. So, it is in two phase region, mixture of liquid as well as vapor. Vapor content is more and liquid content is less. So, this is a container which contains 5 kg of refrigerant R134A. Before cooling, the temperature is minus 18. After cooling, its temperature is minus 26. Dryness fraction is 0.86. Dryness fraction is 0.86. The system uses refrigerant R134A type of, it is a closed system where mass is constant. There is no mass transfer. Process constant volume, because the tank volume remains the same. So, we will assume a constant volume process. From R134A tables. So, today we have used for one problem steam table. Even in one of the earlier classes we were using steam tables for finding out the properties of the steam. So, now this is refrigerant is used. So, we have to use a refrigerant table R134A tetrafluoroethane. So, this is the refrigerant tables and charts. So, here you can see R134A tetrafluoroethane. R134A table I have taken. The temperatures are, first T1 is given as to minus 26. So, corresponding to minus 26, I have taken the liquid entropy and gaseous entropy 0.8704. Liquid entropy is this one, gaseous entropy is this column. So, 0.8704, because this table does not give SFG value directly, So, this is the value. So, the difference between SG and SF will give you SFG. So, from R134A table at minus 18 degrees centigrade, read out SF value. At minus, this is for minus, I have noted for state number 2. Okay, no problem, we will first finish state point 2 and then we will come to state point 1. So, this is at state 2. So, SF2 value I have taken. So, that is 0.8704, and SG2. I am using 2 for final state and 1 for initial state. 1.7476. Now, we can find SFG2, that is equal to SG2 minus SF2. So, that is 1.7476 minus 0.8704. So, this difference gives the SFG value, SFG2 value. So, that is 0.8772. So, this is 0.8772 SFG2. Okay, kilojoule per kg Kelvin. Now, let us take the property value from the R134 table corresponding to the initial state temperature of minus 18. This is minus 26. Let me again repeat. Initial state, the temperature is minus 18, final state is minus 26. First, I have taken for minus 26, then now I am going to take for minus 18 degrees centigrade, that is state 1. State 1. This is state 1. So, I have taken the vapor entropy, assuming it as because it is given as a saturated, you can see saturated. So, the inlet condition is saturated. Outlet is obviously it is not saturated because the dryness fraction is given. So, it is a mixture of liquid and vapor, it is a mixture of liquid and vapor. The inlet condition is saturated vapor at state 1. So, at minus 18 directly I can take the minus 18, I can take the vapor entropy 1.7399. SG1 is equal to 1.7399. So, this is S1. Because the condition of the refrigerant is saturated, see you can write like this, S1 is equal to S of 1 plus X1 into S of G1, S of G1. This is equal to S of 1 plus X1 into S of G1 can be written as SG1 minus S of 1. If it is a saturated vapor, dryness fraction value is 1. So, this becomes S of 1 plus 1 into SG1 minus S of 1. So, if you simplify S of 1 plus SG1 minus S of 1, S of 1 and S of 1 will get cancelled. So, entropy at 1 is equal to gaseous entropy. So, that is what I have written directly here. So, this is a very basic one. Like this we can write enthalpy also, H1 is equal to H of 1 plus X1 into H of G1. The enthalpy at a saturated condition will be Hg1 only. So, this is kilojoule per kg Kelvin, here also kilojoule per kg Kelvin, S1. So, now dryness fraction is given, I can find out the entropy at state point 2. Entropy at state point 2 is equal to S of 2. I can write a similar equation. Before calculating this one, if it is a saturated liquid, X is equal to 0. If it is a saturated vapor, X is equal to 1. If it is between 0 and 1, it means two phase region, mixture of liquid and vapor. Now, S2 is equal to S of 2 plus X2 into S of G2, and the X2 is given in the problem as 0.86. The dryness fraction of the refrigerant after cooling, that is at the end of state 2 is 0.86. Now, we know S of 2, X2 is given, S of G2 we have found, because in the table S of G2 is not there, as I said before. We can find the difference between SG2 and SF2. So, substitute the values, all the values you will get entropy at state point 2, 1.6248, 1.6248 kilojoule per kg Kelvin. So, now the change in entropy during this process is the mass into how much mass is a quantity of refrigerants into the entropy change, M into S2 minus S1. M is given as 5 kg, M is given as 5 kg in the problem. S2 we have found out, S1 we have found out directly from the table because it is saturated vapor. Only for S2 we have to use the formula SF2 plus X2 into S of G2. So, that comes negative. The negative sign indicates that the entropy of the system during the process is decreasing, during the process is increasing. Whenever we have the positive value, it is increasing. Negative value indicates the entropy of the system is decreasing during the process. Which of the following process, let us take another example. Which of the following process is more irreversible? A heat source at 1200 Kelvin, the source temperature is 1200 Kelvin, the sink temperature is 800 Kelvin, it loses 2500 kilojoules of heat, or a heat source at 800 Kelvin loses 2000 kilojoules of heat to a sink at 500. So, in the first case, process 1, source temperature is 1200 Kelvin, source is T1 1200 Kelvin, sink is T2 800 Kelvin, okay. and the amount of heat rejected during the process 1. So, I am writing Q1 as process 1. There are two different situations. The first one I am taking as process 1. So, this is equal to 2500 kilojoules, 2500 kilojoules. Now, the change in entropy for process 1 can be calculated as, this is for process 1. This one does not represent initial state, because we have two different processes. So, the change in entropy for this one is how much heat is rejected by the first one, first process 2500 kilojoule. So, 2500 divided by, let me write the formula, Q1 by T2 minus Q1 by T1. So, if you substitute the value 2500 by 800 minus 2500 by 1200. The temperature is given in Kelvin. So, make sure that you substitute the temperature in Kelvin. So, this is 800 minus 2500 by 1200. So, this is del S1, del S1. So, there is one negative, this one, okay. So, 2500 minus this one. So, you get 1.04, 1.04, okay. So, actually due to some the system compatibility, this term has come here. Actually, this should be this side, this term should be this side, 1.04 kilojoule per Kelvin. This is for process 1. Similarly, calculate for process 2. Similarly, calculate for process 2. For process 2, the source temperature T1 is equal to 800 Kelvin. You can see for process 2, the heat source is at 800 Kelvin and sink temperature is 500 and the amount of heat lost is 2000. So, sink is T2, that is equal to 500 Kelvin, and Q, let us take for process the heat lost is Q2, heat lost in Q2, that is 2000 kilojoule. This is 2000 kilojoule. So, perform a similar calculations, del S2 is process 2. So, instead of Q1 I will write Q2 divided by T2 minus Q2 divided by T1. So, this is equal to Q2 is 2000 divided by T2 is 500 minus Q2 is 2000 divided by T1 is 800. So, if you simplify this one, you will get 2000 divided by 500, so you will get 1.5. So, this term is 4. So, 1.5 kilojoule per Kelvin. So, now if you compare this, the enthalpy change of process 1 and process 2, you will find enthalpy change of process 2. See here it is, let me, this is the enthalpy change of process 2, this is the enthalpy change of process 1. So, del S of 2 is greater than del S of 1, del S of 1, del S of 1. So, what is the question asked? Which of the following is more irreversible? Since the entropy change of process 2 is more than entropy change of process 1, process 2 is more irreversible than process 1. So, this is one practical example which I have taken. So, just to find out amount of heat lost by a device which is operating between a two different heat source, two different source temperature and two different sink temperature, and of course, the heat quantity is also different. So, a similar exercise can be done in case if the amount of heat lost is same by varying the source temperature and the sink temperature. So, to summarize this, what we have discussed in lecture number 5, we started with the development of entropy, how the concept of entropy has evolved, what is Clausius inequality, Clausius, that is a cycle integral of dq by t is equal to 0 for a reversible process, it is less than 0 for a irreversible process, if it is greater than 0 then the process becomes an impossible one. Then we saw what is the entropy generation. The entropy generation, that is the difference between the change in entropy and the entropy transfer, that is a ds minus dq by t, so integral of dq by t for a process 1 to 2. If the entropy change is equal to the entropy transfer, then there is no generation of entropy, that is S gen is equal to 0. S gen is equal to 0. Then we saw the principle of increase of entropy. Then based on these concepts, we have solved a problem. The first problem was for a steam condensation of steam, what is the entropy change. Next one was I took on refrigerant. The refrigerant R134 is cooled from minus 18 degrees centigrade to minus 26 degrees centigrade. Then we solve the entropy of the of that system. And now we have taken, I have taken two different source temperature and two different sink temperature and two different quantity of heat rejected, which process, either the process 1 or process 2 is more irreversible. Since the delta change in entropy or the delta S for process 2 is more than process 1, so the process 2 is more irreversible than process 1. So with this I conclude the lecture number 5. See you in lecture number 6. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.